Beyond the familiar stars lies an immense and empty darkness. This is the cosmic void, a realm of profound mysteries that defy our basic understanding of the universe. It is not merely empty space, but a region filled with secrets that challenge the very foundations of physics and cosmology. By the end of this journey, you will uncover 25 of the most baffling enigmas hidden within this nothingness. We will explore why a colossal sphere of space contains almost no galaxies, and how a strange cold spot in the ancient light of the universe might be linked to a gaping hole in reality. What do you believe is waiting for us in the great dark between the stars? Our first journey into the cosmic emptiness takes us to a place of staggering scale and silence. Known as the Boötes Void, this region is a near-spherical chasm in the cosmos, so vast it could swallow thousands of galaxies like our own Milky Way without a trace. Stretching an almost incomprehensible 330 million light-years across, it was first uncovered in the 1980s, and its discovery sent a shockwave through the world of astronomy. Imagine a bubble in the universe's foam, but one where the material is almost entirely missing. This is not a complete vacuum, of course. A handful of lonely galaxies drift in that immense darkness, but their number is so small that the average distance between them is millions of light-years. This profound emptiness earned the void its haunting nickname, the Great Nothing. The existence of such a void directly challenged our models of how the universe arranges itself on the largest scales. We expect matter to be distributed in a vast cosmic web, with dense filaments of galaxies surrounding emptier pockets, but the Boötes Void is not just a pocket. It is a gaping hole, a statistical anomaly so extreme it seemed almost impossible. How could a region this large contain so little? One leading theory suggests it is simply a cosmic accident, a natural consequence of the universe's lumpy distribution where, by sheer chance, several smaller voids merged into one colossal emptiness. Yet its sheer size and remarkable sphericity push the limits of this explanation, leaving room for more exotic ideas. Some scientists have proposed that its origins might lie in the very first moments of creation, seeded by a massive quantum fluctuation in the primordial energy field that inflated into the staggering void we observe today. Was it born from a random quirk of structure, or is it the fossil of a fundamental event from the dawn of time? The Great Nothing holds its secret tightly, a silent enigma floating in the dark. From the profound emptiness of the Great Nothing, we turn our gaze to another chilling anomaly, one written in the faint afterglow of the universe's birth. In the ancient light that fills all of space, there is a cold spot, a place that should not exist. This is the cosmic microwave background cold spot, a region in the constellation Eridanus that is mysteriously and significantly colder than the rest of the sky. It is a ghost in the machine of creation, a fingerprint of something strange left over from the first moments of time. For years, its existence baffled cosmologists. How could the universe's baby picture have such a glaring blemish? Then, astronomers discovered a potential culprit lurking in the same direction, a vast expanse of relative nothingness called the Eridanus Supervoid. This supervoid is a colossal underdense region, a bubble in the cosmic web where galaxies are few and far between. The proposed explanation is as elegant as it is strange. As light travels through the expanding universe, it must climb out of gravitational wells. When light enters a void, it loses energy climbing in, but then regains that energy as it climbs out. However, in an eternally expanding universe, the void itself is growing, which changes the balance. The light effectively loses a tiny bit of energy overall, shifting to a longer, redder wavelength. For the cosmic microwave background radiation, this means it appears slightly colder after its billion-year journey through the supervoid. It is as if the void itself acts as a cosmic battery, slowly draining the energy from the primordial light. Yet here is where the mystery deepens. The Eridanus Supervoid, as immense as it is, might not be nearly large enough or empty enough to cause the staggering temperature drop we observe. The numbers simply do not add up. The cold spot is too cold. This has led to a fierce controversy. Is the supervoid merely a foreground object that coincidentally lines up with the cold spot, making the anomaly appear more severe than it truly is? Or does its presence point to a far more exotic origin? Some theorists suggest the cold spot could be evidence of a collision with another universe, a cosmic bruise from a reality beyond our own. The void, then, would be a secondary feature, not the primary cause. The debate rages on, leaving us with a fundamental puzzle. Is this cold spot a simple, if poorly understood, cosmic shadow, or is it a window into physics so strange it defies our current comprehension of reality? The debate over a distant cold spot becomes deeply personal when we realize we might be living inside a void of our own. This is the KBC Void, a proposed cosmic underdensity named for the astronomers Keenan, Barger, and Cowie. Their research suggests our Milky Way galaxy sits at the heart of a staggering emptiness nearly 2 billion light-years across, a region significantly less dense than the average universe. We are not in a special, crowded place, but floating in a vast bubble of relative nothingness. This discovery turns our cosmic perspective inside out. For decades, astronomers have worked to measure the Hubble constant, the rate at which our universe is expanding. But a troubling discrepancy has emerged, a conflict known as the Hubble Tension. Different methods for measuring this expansion yield different results, creating a rift in our fundamental understanding of cosmic evolution. One leading explanation points directly to our local environment. If we are truly inside a giant void, it would distort our measurements. Think of it like standing in a valley and trying to measure the slope of the entire continent. Your local terrain would skew your perspective. In cosmic terms, the lower density of matter in our local void would affect the local pull of gravity, subtly altering the apparent speed at which distant galaxies are receding from us. This local underdensity could be the key that resolves the Hubble tension, reconciling the conflicting measurements by accounting for our own unusual address. Yet, the idea remains controversial. Is the KBC Void a real structure or a statistical fluke in how we've mapped the galaxies around us? If it is real, its sheer scale challenges standard models of cosmology, which predict a more uniform universe on such vast scales. The possibility that we live in a cosmic hole forces us to question whether our view of the cosmos is clear, or if we are peering out at the universe from the bottom of a well. What other fundamental truths might be skewed by our lonely location in the great dark? This profound emptiness surrounding us may hold the key to the universe's most elusive force, dark energy. While dark energy drives the accelerating expansion of the cosmos everywhere, its effects are magnified and made most visible within the vast, underdrenched realms of cosmic voids. Think of a void as a nearly empty balloon within the larger balloon of the universe. As the cosmos expands, the emptiness inside the void stretches even faster because there is so little matter and gravity to hold it back. This makes voids perfect natural laboratories, pristine environments where the subtle push of dark energy can be observed without the complicating clutter of galaxies and dark matter. Astronomers are now conducting massive sky surveys, meticulously mapping the shapes and sizes of millions of voids. By measuring how these empty regions have grown and evolved over billions of years, they can trace the history of dark energy's influence. The central question is deceptively simple. Is the strength of dark energy constant, or has it changed over the life of the universe? If it is constant, our current model of cosmology remains intact. But if its strength has varied, everything we think we know about the universe's fate must be rewritten. A changing dark energy could mean the acceleration will eventually stop or even reverse into a catastrophic collapse. It could point toward entirely new physics, a force unlike anything we have yet described. The silent, expanding voids are therefore recording a cosmic tug-of-war, and by listening to their growth, we are tuning into the fundamental rhythm of reality itself. What will these empty spaces tell us about the force that holds the final word on our cosmic destiny? The silent expanses of the cosmic void may be hiding something fundamental, the very atoms that build our reality. Across the universe, a census of ordinary matter, the protons and neutrons known collectively as baryons, has revealed a staggering shortfall. When we add up all the matter we can see in stars, galaxies, and gas, we find only about half of what our models of the Big Bang predict should exist. The rest has simply vanished, creating one of cosmology's most persistent puzzles, the missing baryon problem. So where did half the universe's ordinary matter go? The leading suspect is the vast, empty space between the filaments of the cosmic web. Theorists propose that a significant portion of these lost atoms are drifting in the form of a diffuse, superheated fog known as the warm-hot intergalactic medium, or WIM. This is not a cold, empty vacuum, but a sea of incredibly thin gas, heated to temperatures of hundreds of thousands, even millions of degrees. It is so tenuous that a single cubic meter of this space might contain only a few atoms, making it virtually invisible to our telescopes. How do you find something that is everywhere yet almost completely transparent? Astronomers have devised a clever method using the universe's most powerful flashlights, quasars. These are the intensely bright cores of distant galaxies, and their light travels for billions of years to reach us. As this light passes through the cosmic voids and the filaments of the WIM, the specific elements in that hot gas, like oxygen and neon, absorb very particular colors from the quasar's brilliant white light. By the time the light arrives at our telescopes, it is imprinted with a faint barcode of missing colors, the spectral fingerprints of the WIM. Each absorption line is a direct detection of that elusive matter, a shadow cast by the invisible stuff that fills the voids. Finding these faint signals is like trying to hear a whisper in a hurricane, requiring the most sensitive instruments on Earth and in space. Yet, piece by piece, the evidence is mounting. The great voids are not truly empty. They are reservoirs holding the lost inventory of the cosmos in a form so subtle we are only just learning to see it. What other secrets are written in the light that journeys through the great dark? These lost atoms drift through the emptiness, yet some of them do not remain alone. In the profound isolation of the cosmic void, a few galaxies have managed to form, and they are unlike any others. These are the void galaxies, rare islands of stars adrift in an ocean of nothingness. Cut off from the bustling crowds of galaxy clusters, their existence is a puzzle in itself. How does a galaxy form with almost no raw materials to build upon? The answer lies in their unique environment. Because they are so isolated, void galaxies are often rich in the one resource that fuels star formation, cold hydrogen gas. In the dense urban centers of galaxy clusters, this gas is often stripped away by violent interactions with neighbors or heated to extreme temperatures by the cluster's own environment. But in the quiet countryside of the void, this gas can accumulate undisturbed, providing a pristine fuel reserve for billions of years. This isolation leads to some truly strange evolutionary path. Some void galaxies appear to be living fossils, ancient and undeveloped, because they have experienced so few mergers or collisions. They are like time capsules from the early universe, preserving conditions that have long since vanished elsewhere. Others, paradoxically, can experience intense, albeit delayed, bursts of star formation. With a vast reservoir of gas and no disruptive neighbors, a single event, perhaps the gentle accretion of a small cloud, can trigger a firestorm of new star birth, making a void galaxy suddenly appear younger and more vigorous than its crowded cousins. Their very shapes can be unusual, often showing disturbed or irregular structures not because of outside forces, but because of their own internal, lopsided growth. Studying these galactic hermits is like running a controlled experiment on galaxy evolution. By observing how stars form in the ultimate low-density environment, free from the chaos of crowds, we can isolate the fundamental processes that govern all galaxies. The void galaxies ask us a profound question. Is the violent, interactive life in a cluster the normal path for a galaxy? Or is the quiet, isolated existence in the void its purest, most natural state? The strange existence of void galaxies reveals a deeper truth about the cosmos. Emptiness is not random. It is structured, forming the very skeleton of the universe. We call this the cosmic web, a vast, interconnected network of galaxy filaments surrounding immense, empty bubbles. But these voids are not all the same. They possess their own hidden architecture, a void hierarchy that is one of the most profound mysteries of the large-scale universe. Picture a cosmic foam where tiny bubbles cluster inside larger ones, which themselves drift within continent-sized empty regions. This nested structure, from small underdensities barely visible to us all the way up to the colossal voids like the one in Boötes, forms an intricate ladder of nothingness. How did this hierarchy emerge from the fiery chaos of the Big Bang? The answer is written in the first moments of time. In the primordial universe, tiny quantum fluctuations, random ripples in the density of energy and matter, were stretched to astronomical proportions during a period of hyper-expansion called inflation. These ripples became the seeds for all future structure. Where the density was slightly lower than average, that region would evolve into a void as gravity pulled matter away toward the higher density peaks. The specific pattern of these initial ripples, their strength and size, dictated the final foam-like structure we see today. The void hierarchy is a direct fossil of those first quantum whispers. This is why mapping the empty spaces is so crucial. By carefully measuring the sizes and distributions of voids from the smallest to the largest, cosmologists can perform a fundamental test. They can compare the observed hierarchy against predictions from different models of inflation and the Big Bang. Does the cosmic foam match what the simplest models of inflation tell us it should look like? Or do we see anomalies, voids that are too large or too spherical, that could force us to rewrite the story of the universe's birth? The grand tapestry of galaxies is only half the story. To truly understand our origins, we must also learn to read the silent, empty spaces in between. These silent voids may hold an echo from the very beginning of everything. The largest cosmic voids could be preserving a faint imprint of primordial gravitational waves, ripples in the fabric of space-time generated in the first fleeting instants after the Big Bang. During the period of hyper-expansion called inflation, the universe is thought to have undergone a violent stretching, and this process would have sent powerful waves coursing through the very structure of reality. These waves are not made of matter or energy, but are literal vibrations of space and time itself. For over 13 billion years, they have been propagating through the cosmos, a relic from its absolute birth. But how could we possibly detect such a subtle signal? The answer may lie in the emptiness. As these primordial ripples passed through the early universe, they would have subtly compressed and rarefied the distribution of matter. Think of it like a sound wave traveling through air, creating areas of high and low pressure. The gravitational waves would have created a corresponding pattern in the density of the cosmos, a pattern that was then frozen into place as the universe expanded and cooled. The regions of lowest density, the seeds of the largest voids, would have been permanently shaped by this ancient vibration. Their specific arrangement, their sizes, and even their slightly preferred elongated shapes could all carry the signature of those first spacetime tremors. Future observatories like the Laser Interferometer Space Antenna, or LISA, are designed to detect gravitational waves from merging black holes, but to hear the whisper from the beginning, we may need a much larger instrument. The cosmic voids themselves could act as that instrument, a natural antenna of staggering scale. By meticulously mapping the three-dimensional shapes and orientations of thousands of the largest voids, Astronomers hope to find a statistical pattern in their alignment, a collective preference for a certain direction that can only be explained by the passage of those primordial waves. Finding this signal would be like discovering the fossilized footprint of creation. It would provide direct, incontrovertible evidence for cosmic inflation and open a window into a realm of physics so extreme it is currently beyond our reach. What secrets about the universe's first moment are encoded in the vast, empty spaces between the galaxies? This silent architecture of emptiness may be actively shaping the galaxies that border it. Astronomers have uncovered a bizarre phenomenon involving the thousands of galaxies that form the outer walls of cosmic voids. These galaxies are not oriented randomly. Instead, their spins, the axes around which they rotate, appear to be aligned with each other in a vast, coherent pattern, as if choreographed by the void itself. Picture a colossal, slowly spinning bubble with the galaxies on its surface all leaning in the same direction. This discovery is deeply unsettling. According to our standard model of cosmology, the universe should be largely isotropic, meaning it should look the same in every direction on the largest scales. The initial conditions of the Big Bang should have sent galaxies spinning in a chaotic, random fashion. Finding such a large-scale, organized alignment is like throwing 1,000 tops into the air and watching them all spin on the same tilted axis. It should not happen, so what cosmic force could be responsible for this strange coordination? The leading suspect is the void's own gravitational influence, specifically its tidal forces. As a void expands, it creates a subtle gravitational gradient. Matter is pulled more strongly toward the dense filaments surrounding the void than into the empty center. This tidal effect can gently torque the galaxies forming on the void's edge, influencing the direction of their angular momentum over billions of years. It is a slow, cosmic dance where the emptiness itself leads. This presents a serious challenge. Our current understanding of gravity, governed by Einstein's theory of general relativity, can produce tidal forces, but whether they are powerful enough on such vast scales to create the alignments we see is a matter of intense debate. The presence and distribution of dark matter are crucial here, as it provides the primary source of gravity that shapes these tidal fields. If the observed alignments are real and widespread, they might indicate that dark matter interacts or is structured in ways our models do not predict. Alternatively, it could be a hint that our understanding of gravity itself needs revision on the largest scales, perhaps pointing toward more exotic theories. The spins of these galaxies are like cosmic compass needles, and they are all pointing toward a hidden force we do not yet fully understand. What is the void whispering to the galaxies that surround it, and what does that message reveal about the true nature of gravity and the dark universe? These organized spins on the edge of emptiness lead us to an even more profound possibility. The cosmic void is more than a structure. It is a pristine laboratory for uncovering physics that operate in the shadows. Within these near-vacuum environments, the subtle signatures of exotic particles and forces, otherwise drowned out by the noisy gravity of dense matter, could finally become visible. One of the most sought-after prizes is the action, a hypothetical particle that is a leading candidate for the mysterious substance we call dark matter. In the crowded space of a galaxy cluster, the effects of individual actions would be impossible to untangle from the collective gravitational pull. But inside a vast void, where the influence of normal matter and even standard dark matter is minimal, the unique way actions might interact with light could create a faint, detectable signal. It is like trying to hear a single violin in a roaring rock concert. The void turns down the volume on everything else, allowing that one delicate note to be heard. Another exotic idea involves chameleon fields. These are hypothetical forces that change their strength based on the density of their environment. In a place full of matter, like Earth or a star, the chameleon effect would be incredibly weak, hiding it from our experiments. But in the deep emptiness of a cosmic void, where the density is 1 billion times lower, the field could reveal its true nature, exerting a subtle force on the matter and light within the void. How could we possibly detect such a phantom? The answer lies in the void's own shape and the light that passes through it. A chameleon field or the presence of actions would cause subtle yet measurable distortions. The void's spherical form might appear slightly squeezed or stretched in a specific way. Even more telling, the light from distant galaxies shining through the void would not travel in a perfectly straight line. The exotic fields or particles would bend its path in a unique fingerprint, an effect called weak gravitational lensing. By mapping the void with extreme precision and studying how it warps the background tapestry of the universe, astronomers are effectively conducting a deep field scan for the invisible components of reality. The great voids are asking us a fundamental question: is our catalogue of particles and forces complete, or are we surrounded by a hidden world of physics, waiting to be discovered in the quietest places in existence? The profound emptiness of the void might even warp the flow of time itself. Einstein's theory of general relativity gives us a startling rule: gravity is the master of time. The stronger the gravitational field, the slower time passes. This is not just a theory, it is a measured reality. The GPS satellites orbiting Earth high above our planet's gravity must have their clocks constantly corrected because they tick ever so slightly faster than clocks on the ground. Now consider a cosmic void, a region of such extreme low density that its gravitational pull is almost negligible. According to the same physics, time within that void should run faster than it does in our galaxy-rich neighborhood. A clock placed in the heart of the Boötes Void would, over billions of years, gradually gain time compared to a clock here. This leads to a dizzying cosmic perspective. The universe does not have a single universal clock. The history of the cosmos is being recorded at different rates in different places. In the dense, violent cores of galaxy clusters, time is stretched out, slowing to a crawl. In the serene emptiness of the voids, it rushes forward. But does this temporal gradient have any real, observable effect? One potential consequence involves the light from distant supernova, which we use as cosmic mile markers to measure the universe's expansion. This light originates in regions of varying density and therefore different flows of time. If we do not account for this, could it subtly distort our measurements of cosmic distances and the very expansion history we are trying to unravel? The idea remains speculative, a theoretical ripple from Einstein's equations, yet it forces us to confront a strange truth. The great story of the universe is not being told at a single speed. From our vantage point, surrounded by a typical amount of matter, we are witnessing a version of cosmic history played out at a specific tempo. But in the deep voids, that same history is on fast forward, a silent, accelerated timeline unfolding in the dark. The silent voids might be the universe's most powerful particle accelerators. Deep within their immense, empty frontiers, a collision of titans could be taking place. As cosmic voids expand over billions of years, their outer walls, made of dark matter and galaxies, eventually meet. When these vast, underdense regions merge, they generate colossal shock waves that ripple through the intergalactic medium. Theorists propose that these invisible tsunamis could act like natural versions of our largest atom smashers, but on an unimaginable scale. Within these shocks, charged particles like protons could be accelerated to velocities approaching the speed of light, gaining energies millions of times greater than anything we can produce here on Earth. We call these mysterious projectiles ultra-high-energy cosmic rays. They are the most energetic particles ever observed, each one carrying as much punch as a professionally thrown baseball, all compressed into a single subatomic speck. Yet for all their power, they are incredibly rare, striking Earth's atmosphere only about once per square kilometer per century. Their rarity is only the beginning of the mystery. The true puzzle lies in tracing them back to their source. These particles are electrically charged, which means their paths are bent and twisted by the magnetic fields that permeate the cosmos. By the time one reaches us, it is impossible to simply look back along a straight line to see where it came from. It is like trying to find the origin of a leaf carried by a twisting, turbulent river. This is where the voids offer a new path to an answer. If these merging voids are indeed the factories for ultra-high-energy cosmic rays, they would not produce them in isolation. The same violent process would also create a burst of neutrinos and gamma rays. Unlike charged particles, neutrinos travel in perfectly straight lines, completely ignoring magnetic fields, while gamma rays are only slightly deflected. By building observatories that can detect these different cosmic messengers at the same time, we can perform a form of triangulation. When a high-energy cosmic ray arrives, we would search the sky for a matching neutrino or gamma ray signal coming from the same direction. If that direction consistently points toward the intersecting walls of merging cosmic voids, we will have found our culprit. Mapping the vast architecture of emptiness is therefore not just about understanding structure. It is about hunting for the engines of the most violent and enigmatic events in the universe. What other unimaginable forces are stirring in the quietest places we know? Deep within the cosmic voids, a new layer of mystery unfolds with the galaxies that are not there. We might expect these vast, empty regions to be sprinkled with tiny, faint dwarf galaxies, the smallest and most common building blocks of the cosmos. Yet many voids appear to be completely sterile, lacking even these diminutive stellar systems. This absence is as telling as a presence, pointing to a fundamental failure in the process of cosmic structure formation. How does an entire region of space, spanning hundreds of millions of light-years, fail to produce even the smallest of galaxies? The answer likely lies in the very beginning, during the epoch of reionization. In the first billion years after the Big Bang, the first stars and galaxies ignited, flooding the universe with intense ultraviolet radiation. This radiation heated the diffuse hydrogen gas throughout the cosmos, stripping electrons from atoms in a process that made the gas too hot and energetic to easily collapse and form new stars. In the dense environments of the future cosmic web, gravity was strong enough to overcome this and pull the gas together. But within the proto-voids, the gravitational pull was inherently weaker. The seeds for dwarf galaxies in these regions, the small dark matter halos, simply did not have the strength to capture and hold onto the heated gas. It was a cosmic drought from which these regions never recovered, leaving them permanently starved of the material needed to light up. This explains the profound emptiness of some voids, but it deepens the puzzle of others. Why do a handful of voids, against all odds, contain a few isolated dwarf galaxies? This suggests that the initial conditions were not perfectly uniform. Perhaps a small, local overdensity of dark matter provided a deep enough gravitational well to shield a pocket of gas from the pervasive radiation, allowing it to cool and eventually form stars long after the rest of the void was sterilized. These lone dwarf galaxies are then cosmic survivors, having formed against incredible odds in an environment that actively suppressed their very existence. Their unique properties, their ancient stellar populations, and their quiet, isolated lives offer a stark contrast to dwarfs in crowded clusters. They are the ultimate test cases for understanding the minimum requirements for a galaxy to be born. The void-dwarf connection forces us to ask, is the emptiness we see a primordial condition, a fossil from the universe's first light, or is it a dynamic state that could, under the right circumstances, have been filled? These silent echoes from the beginning of time are not just ripples in space-time, but literal sound waves thundering through the newborn cosmos. In its first few 100,000 years, the entire universe was a seething, opaque plasma, a dense soup of particles and light. Within this hot fluid, gravity tried to pull matter together into clumps, while the intense pressure of radiation fought to push it apart. This created a tug of war that generated powerful spherical sound waves, ripples of overdensity that raced outward from every initial fluctuation at more than half the speed of light. We call these primordial vibrations barren acoustic oscillations. Then, the universe cooled just enough for atoms to form, allowing light to travel freely in an event we call recombination. In that instant, the music stopped. The sound waves froze in place, imprinting their signature onto the cosmos. Each wave left a lasting monument, a spherical shell of matter with a specific radius, a preferred scale woven into the fabric of reality. Today, that fossilized echo manifests as a subtle statistical tendency. When we map the cosmos, we find that galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years, which is the radius of that ancient shell. And at the very center of these immense fossilized bubbles, you will often find a cosmic void. The void is the hollow core from which the primordial sound wave expanded. This makes the cosmic voids and the shells of galaxies that surround them a cosmic standard ruler, because we know the original physical size of that sound wave from fundamental physics. We know how big these spherical structures should be. By measuring how much they appear stretched or compressed in the sky at different distances, and therefore different eras in cosmic history, we can trace how the universe itself has stretched over billions of years. It is like finding a ruler of known length embedded at different depths in an expanding balloon. By seeing how the ruler looks to us, we can measure the expansion rate of the balloon itself. This is one of the most powerful tools in modern cosmology. While supernovae give us point measurements of expansion, and the cosmic microwave background gives us a single snapshot of the infant universe, the barren acoustic oscillations traced by voids provide a continuous record, a timeline of expansion etched into the large-scale structure of space. Every vast emptiness surrounded by its faint shell of galaxies is a calibrated marker, a silent witness to the rhythm of the universe's growth. What other fundamental constants are written into the architecture of nothingness? This grand cosmic structure, the very fabric of our reality, might itself be floating within a far greater emptiness. Could our entire observable universe, with all its billions of galaxies and vast cosmic web, simply be a single bubble in an infinite foam? This is the staggering possibility of a metaverse void, a concept that challenges one of cosmology's most cherished principles. The cosmological principle states that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same everywhere and in every direction, with no single location being special or central. This is the foundation upon which all of modern cosmology is built. But what if we are the exception? What if our entire cosmic horizon is contained within a single, unimaginably vast void inside a much larger and perhaps denser metaverse? This would mean we are not in a typical place at all, but in a cosmic backwater of staggering proportions. Such a scenario could potentially explain some of the anomalies that nag at astronomers. The slight but persistent cold spot in the cosmic microwave background, the puzzling Hubble tension in expansion measurements, even the apparent low density of our local universe hinted at by the KBC Void, all of these could be natural consequences of our location. If we are inside a giant underdensity, our view of the cosmos would be fundamentally skewed. Our measurements of the universe's expansion rate would be affected by the local gravitational environment of this colossal void, just as a person in a valley misjudges the slope of a continent. The cosmic microwave background's temperature variations could be partially a reflection of our own unusual address, a local shadow cast by the immense emptiness beyond our observable horizon. Of course, this idea remains highly speculative, a fringe theory that pushes the boundaries of cosmology. There is no direct evidence for such a metaverse, and many scientists strongly defend the cosmological principle as the most logical and elegant foundation for our models. Yet, the mere possibility forces a profound philosophical shift. It asks us to consider that the entire tapestry we have mapped, from the first stars to the largest voids, might be just a single thread in an immeasurably grander design. Are we truly seeing the universe as it is, Or are we merely studying the walls of our own cosmic cave, mistaking its shadows for the whole of reality? This subtle warping of light offers a direct window into the distribution of all matter, both seen and unseen. Gravitational lensing, one of Einstein's most dramatic predictions, occurs when the fabric of space-time is warped by mass, bending the path of light from distant galaxies. We are accustomed to the dramatic effects of massive galaxy clusters, which act as cosmic magnifying glasses, twisting background galaxies into brilliant arcs. But within the cosmic void, the opposite phenomenon occurs. Here, the profound lack of mass creates a different kind of distortion, a demagnification. Instead of being focused, light traveling through a void is subtly diverged, its path bent away from the emptiness. The result is a faint but measurable negative lensing effect, where background galaxies appear just slightly smaller and fainter than they otherwise would. It is as if the void is a weak cosmic defocusing lens, a lens of nothingness. This effect provides astronomers with a powerful scale. By measuring the precise amount of this demagnification, we can effectively weigh the void. We can calculate the total gravitational pull, and therefore the total amount of matter, both dark and visible, that must be present to cause the observed bending of light. Yet here lies a deep and growing puzzle. When scientists perform this cosmic accounting, the numbers frequently do not align. The measured demagnification is often weaker than what our standard models predict. Based on the size and structure of a typical void, we expect a certain amount of dark matter to be present, shaping its gravitational field. But the faint lensing signal suggests there is less matter there than there should be. This is the void lensing anomaly. It forces us to confront two unsettling possibilities. The first is that our understanding of dark matter's behavior within these vast empty regions is flawed. Perhaps dark matter particles interact with each other in ways we do not anticipate, preventing them from accumulating in voids as our models suggest. Or, even more radically, it could point to a need for a modification of the laws of gravity themselves on these immense scales. Our theory of gravity, general relativity, has passed every test with flying colors within the solar system and in dense galactic environments. But is it possible that in the deepest voids, where the gravitational field is almost zero, the rules change in a subtle way? Could gravity behave differently in the presence of near-total nothingness? This anomaly is a quiet whisper from the emptiness, a faint signal that our most fundamental understanding of mass, gravity, and the cosmos may have a critical blind spot. What is truly shaping the light that journeys through the great nothing? These vast, silent voids may have been the last places in the universe to see the first light. We must travel back to the epoch of reionization, a pivotal chapter when the first stars and galaxies ignited, flooding the cosmos with fierce ultraviolet radiation. This radiation systematically burned away the primordial fog of neutral hydrogen that filled all of space, transforming the universe from an opaque sea into the transparent expanse we see today. But this cosmic dawn did not happen everywhere at once. Think of a vast landscape at sunrise where the high mountain peaks are the first to be illuminated, while the deepest valleys remain shrouded in shadow for hours longer. In the cosmic context, the dense knots and filaments of the early cosmic web were those mountain peaks, their intense radiation quickly clearing their local neighborhoods. The voids, however, were the deepest valleys. With so few early galaxies to act as lighthouses, the process of reionization within these empty regions would have been dramatically slower. This leads to a profound mystery. Were cosmic voids the final bastions of neutral hydrogen, holding out against the encroaching light for hundreds of millions of years after the rest of the universe had become transparent? If so, these regions would have been cosmic time capsules, preserving the pristine conditions of the Dark Ages long after they had vanished elsewhere. The implications are staggering. If the last pockets of neutral hydrogen lingered in the voids, they would have subtly imprinted their signature on the light that later traveled through them. The most promising way to detect this fossil signal is by observing the most distant objects we can find, quasars from the early universe. As their light journeys for billions of years to reach us, any remaining patches of neutral hydrogen in the voids along the line of sight would absorb specific telltale wavelengths, creating a unique absorption fingerprint in the quasar spectrum. Finding this signature would be like discovering a fossilized bubble of the infant universe. Next-generation telescopes, like the James Webb Space Telescope and the upcoming extremely large telescopes on the ground, are our time machines for this very purpose. They have the power to peer into the most distant voids to the very edge of the observable universe and search for these final shadows of the cosmic fog. By mapping when and where the voids finally became reionized, we can reconstruct the entire timeline of this universal transformation. Did the lights turn on slowly and unevenly, with the voids flickering on last, or was the process more violent and rapid? The answer is written in the emptiness. Solving this mystery would tell us not just about the voids, but about the nature and distribution of the very first galaxies, the engines that lit up the cosmos. The great voids ask us, were they the final frontiers of the cosmic dark, the last places to surrender to the dawn? This continuous flow of matter carves the very structure of the cosmos. The voids are not static, empty bowls. They are dynamic engines functioning as colossal cosmic conveyor belts. Over billions of years, matter steadily drains from these underdense regions, streaming outward along the invisible filaments of the cosmic web. This grand exodus flows directly into the dense nodes of the universe, the galaxy clusters and superclusters, feeding their growth like rivers flowing into an ocean. This vast, slow-motion river of gas and dark matter is driven by the simplest of forces, gravity. The dense regions simply have a stronger gravitational pull, relentlessly tugging material away from the emptier voids. We can actually observe this through subtle distortions in the light of distant galaxies, a phenomenon known as redshift space distortions, which reveal the velocity of this cosmic drift. The mystery is not that this flow exists, but what it does to the galaxies caught in its current. A galaxy living on the edge of a void, slowly being pulled toward a dense cluster, experiences a profoundly different life from one that remains in the quiet interior. As it journeys along the filament, it is subjected to increasing tidal forces and mounting pressure from the intergalactic medium. This can strip away its precious reservoir of cold gas, the very fuel for new stars, effectively quenching its star formation and turning a vibrant blue spiral galaxy into a passive, red and dead entity long before it even reaches the cluster's chaotic core. The conveyor belt does not just transport galaxies, it fundamentally reshapes them. This leads to a pivotal question about the dark matter that comprises most of this flowing mass. Our simulations of the cosmos rely on certain assumptions about how dark matter behaves, specifically that it is cold and collisionless, meaning particles of dark matter pass right through each other. The observed large-scale flows generally match these simulations, but there are intriguing subtleties. The precise speed and distribution of this matter movement could reveal hidden properties of dark matter. If the flows are slightly faster or more coherent than our models predict, it might suggest that dark matter particles can interact with each other in a very slight way through some unknown force. Alternatively, it could point to the influence of another unseen component, like massive neutrinos, subtly altering the gravitational landscape. By meticulously charting these cosmic currents, we are conducting a fundamental test. Does the universe's conveyor belt operate exactly as our standard model dictates, or is its rhythm hinting at a deeper, more complex physics governing the dark sector? The silent, outward rush from the voids is more than just an architectural process. It is the pulse of the cosmic web, and its beat may be telling us a story we have only just begun to hear. Floating in the profound emptiness of the voids are cosmic ghosts, dense spheres of ancient stars with no galaxy to call home. These are isolated globular clusters, and their existence is a deep and haunting puzzle. Globular clusters are typically found in the bustling halos of large galaxies like our own Milky Way, each one a glittering city of up to 1 million stars, all bound together by gravity and dating back to the universe's infancy. To find these ancient relics adrift in the void, completely alone, defies our expectations of where they belong. How did these stellar cities become cosmic orphans, cast adrift in the great dark? One compelling theory points to a violent past. During the chaotic mergers of galaxies, the gravitational forces involved are titanic. It is possible for a globular cluster, a relatively small and dense object, to be slingshotted out of its host galaxy entirely, flung into the intergalactic void at tremendous speed. This ejection would sever its gravitational ties forever, leaving it to wander the emptiness as a lone, starry wanderer. Yet another, perhaps even more dramatic, theory suggests these clusters are not orphans at all, but survivors. They may be the last remaining hearts of ancient dwarf galaxies that ventured too close to a larger, predatory galaxy. In such an encounter, the overwhelming tidal forces can slowly and completely strip away the dwarf galaxy's outer stars and dark matter halo, leaving behind only its dense, resilient core, the globular cluster, as the sole testament to a galaxy that was utterly consumed. This makes the isolated cluster a galactic tombstone, marking the spot where a small galaxy met its end. Their presence in the void is therefore a silent record of ancient cosmic violence. By studying the ages, compositions, and motions of these isolated clusters, astronomers can perform a form of celestial archaeology. Each one holds clues that could reveal whether it was violently ejected from a galactic crash or if it is the lone survivor of a cannibalized dwarf. These stellar hermits force us to reconsider the life cycle of the universe's smallest structures. Is the void a dumping ground for galactic debris, or is it a graveyard filled with the ghosts of long-dead galaxies? Their ancient light, shining in the deepest emptiness, tells a story of loss and survival on a cosmic scale. The temperature of the void holds a secret that defies simple intuition. One might assume that the most empty places in the universe would be the coldest, a perfect cosmic deep freeze. Yet, observations reveal a baffling correlation. The larger the void, the hotter the gas within it seems to be. This is not the concentrated heat of a star, but a diffuse, superheated fog where individual atoms are whipping around with tremendous energy, despite being separated by vast distances. How can nothing be so hot? The answer lies in the violent history of the void's own growth. As a colossal void expands over billions of years, its outer walls, made of dark matter and galaxies, exert an immense gravitational pull on the sparse material inside. This matter, mostly hydrogen gas, is accelerated outward, rushing toward the edges, but the void is expanding faster than the gas can flow. This creates a cosmic traffic jam, a colossal shock wave that forms along the void's boundary, slamming into the infalling gas and heating it to temperatures of tens of millions of degrees. It is a sonic boom on a universal scale, a permanent roar of energy generated by the emptiness itself. There is another potential furnace at work. Over the eons, the supermassive black holes at the centers of the few galaxies within or near the void can go through active phases, spewing unimaginable amounts of energy in the form of jets and radiation. In a dense environment, this energy is quickly absorbed, but in the void, with so little material to soak it up, this energy can permeate the entire vast volume, gently cooking the sparse gas over billions of years and contributing to its high temperature. This void temperature relationship is far more than a curiosity. It is a critical piece of the universe's energy budget, a ledger of how heat is distributed and stored across cosmic history. By measuring the temperature of the gas in voids of different sizes, we are effectively reading a historical record of the energetic processes that have shaped the cosmos. Are we seeing the primary signature of void expansion shocks, or is it the accumulated whisper of countless black hole outbursts? The heat in the great nothing is a fossil of cosmic activity, a reminder that even emptiness holds the memory of violence. Even the word void might be a cosmic misdirection, suggesting an absolute emptiness that simply does not exist. This brings us to a foundational mystery that challenges our very vocabulary for the cosmos. What precisely defines a void? Is it a true vacuum or merely a region where the density of matter dips below a certain arbitrary threshold? Astronomers grapple with this question daily, for the answer shapes our entire census of the universe's large-scale structure. There is no universal agreement on the exact density cutoff that separates a void from a mere underdensity. One survey might classify a region as a void if it contains only 10% of the universe's average density, while another might use a more lenient 20%. This seemingly minor technicality has profound consequences. Alter the definition, and the number of voids in the observable universe can change by thousands. Their apparent sizes and distributions shift, and with them, the statistical conclusions we draw about the cosmos's evolution and composition. The boundary of a void is not a sharp, clean line like the edge of a bubble. It is a gradual, fuzzy transition zone where the profound emptiness slowly gives way to the faint tendrils of the cosmic web. Imagine standing in a vast, open plain and trying to pinpoint the exact moment you enter a forest. The trees become more frequent, the canopy begins to close overhead, but there is no single step that marks the boundary. The cosmic web is the same. We assign names void, filament, wall to help our minds grasp the structure, but nature recognizes no such categories. This ambiguity forces a deeper philosophical question. Are we, in our mapping, discovering the universe's true architecture, or are we simply imposing our own human-made grids and labels upon a seamless, continuous reality? The voids teach us that the borders we draw in space are as much a product of our definitions as they are of the universe itself. How many other cosmic truths are hidden, not by darkness, but by the limitations of our own categories? These silent, expanding voids are more than just structures. They are the architects of the universe's final destiny. In a cosmos increasingly dominated by the repulsive force of dark energy, these empty regions are expanding faster than everything else, accelerating the great unraveling of the cosmic web. The fate of all things may be written in their growth. As dark energy continues to push the universe apart, the voids will grow ever larger, their boundaries stretching until they begin to merge with one another. First, smaller voids will combine into larger ones, and then these colossal emptinesses will themselves coalesce. Over trillions of years, the intricate filaments and walls of galaxies that form the universe's beautiful architecture will be stretched, thinned, and ultimately severed. We are heading toward a future where all of existence could become one single, ultimate void. This is the basis for one of the most dramatic end-of-time scenarios, the Big Rip. In this model, dark energy does not just accelerate expansion, it grows in strength over time. Eventually, its push would become so powerful that it overwhelms every force that holds things together. Long before the cosmic web is torn apart, the expansion would rip galaxies from their clusters, then stars from their galaxies. In the final, terrifying moments, planets would be shredded from their stars, and even atoms themselves would be torn asunder, ripped into a soup of fundamental particles scattered across an infinite, lonely darkness. It is a truly ultimate end, the complete dissolution of structure. This is not mere speculation. It is a hypothesis we can test by studying the voids we see today. By meticulously measuring the rate at which voids are growing, we can gauge the strength and constancy of dark energy. Are voids expanding at a steady, accelerated rate, or is that acceleration itself increasing? The answer tells us which future we are heading toward, a slow, cold heat death, or this violent, explosive finale. Every map of the cosmic emptiness is a page from the universe's final chapter. The silent voids are not passive bystanders in cosmic history. They are the active force that will one day consume it. What will their relentless expansion ultimately say about the end of everything we know? Before the first stars ignited, the universe was a silent, dark expanse filled with neutral hydrogen. This era, known as the cosmic dark ages, holds a secret waiting to be heard. A faint radio whisper emitted by that primordial hydrogen should still echo through the cosmos at a specific wavelength. This signal is our most direct link to the universe's infancy, a pristine record of a time before light. To hear this ancient murmur, we must listen to the quietest places we know, the cosmic voids. In these vast empty regions, the signal is protected. It remains uncontaminated by the radio noise from billions of later stars and galaxies, a pure tone from the dawn of time. But detecting it is one of the greatest challenges in modern astronomy. This is not a strong, clear broadcast. It is an incredibly subtle shift in the background radio static of the universe, a signal so faint it is drowned out by our own terrestrial radio stations, satellite transmissions, and even the gentle radio glow from our own Milky Way. Astronomers are building revolutionary instruments in some of the most remote locations on Earth to hunt for this whisper. Massive arrays of radio telescopes are being constructed in deserts and remote valleys, places shielded from human interference. They are not looking for a single point in the sky, but mapping the entire cosmic background, searching for a specific, all-encompassing ripple that signifies the collective voice of that primordial hydrogen. The prize for success would be a transformation of our understanding. This signal would act as a cosmic thermometer, telling us the exact temperature of the universe just a few 100 million years after the Big Bang. It would map the very first ripples in the fabric of reality, the tiny density variations that would one day grow into galaxies, clusters, and the vast cosmic web we see today. By tuning into the voids, we are attempting to build a radio telescope of staggering scale, using the emptiness itself as a silent chamber to isolate the universe's first breath. What will this ancient whisper tell us about our own deepest origins? Deep in the cosmic past, a void defies the timeline of creation. At a redshift of about 1, which translates to a time roughly 8 billion years ago, astronomers have found a colossal bubble of nothingness that simply should not exist. This ancient void is staggeringly large and profoundly empty, a gap in the cosmic web that appears far too mature for the universe's age at that epoch. Its discovery sends a tremor through our understanding of how structure evolves. According to our most trusted models, the universe needs time for gravity to do its work. Dense regions slowly attract more matter, growing into the great clusters and filaments we see, while the underdense regions expand and empty out, gradually becoming the voids we recognize. This process is a cosmic ballet measured in billions of years. Finding a void of such immense scale and emptiness only 8 billion years after the Big Bang is like finding a vast, weathered canyon in a landscape that is supposedly still young. It suggests that the seeds for this immense emptiness were planted much earlier and grew much faster than anyone predicted. One radical possibility is that the initial conditions of the universe were far more varied than we thought. The quantum fluctuations from inflation that seeded all structure might have included some exceptionally large and deep underdensities, cosmic accidents on a grand scale that inflated into premature voids. Another, more unsettling idea is that an unknown form of physics was at play, perhaps a unique interaction involving dark matter or dark energy that accelerated the evacuation of these regions in the universe's youth. This anomalous void is not just a curiosity, it is a direct challenge, a fossil from a younger cosmos that refuses to fit neatly into our simulations. Does its existence mean we must rewrite the early chapters of cosmic history, or does it point toward a richer, more complex set of rules governing the growth of nothingness? This ancient emptiness holds a secret about the tempo of the cosmos, a rhythm that seems to have been far more dynamic and urgent in its youth than we ever dreamed. This profound cosmic isolation leads us to the final and perhaps most human of all the void's mysteries. Could the vast, quiet emptiness between the galaxies be the ideal sanctuary for intelligent life? The violent cores of galaxy clusters are cosmic war zones with frequent galactic collisions, intense radiation from quasars, and deadly gamma-ray bursts that would sterilize entire systems. In contrast, a void galaxy drifts in serene solitude, its planetary systems largely untouched by such external chaos for billions of years. This unparalleled stability could provide the extended, peaceful timeline necessary for life to not only emerge but to evolve into intelligence and build a lasting civilization, all without the constant threat of celestial catastrophe. Yet, this same isolation presents a devastating paradox. Life as we know it requires a rich supply of heavy elements, atoms like carbon, oxygen, and iron forged in the violent deaths of earlier stars. These elements are scattered throughout space by supernova explosions, seeding new generations of stars and planets. In the crowded galactic cities, this process happens rapidly, with stellar generations quickly enriching the cosmic environment. But in a void galaxy, the stellar population is so sparse and supernovas so rare that this essential recycling of elements may happen at a glacial pace. A planetary system forming in a void might be born from gas that is primordial and impoverished, lacking the very building blocks for rocky planets or the complex chemistry that life requires. The void could be a cosmic desert, beautiful and peaceful, but ultimately sterile. So we are left with a haunting question, one that bridges the vast science of cosmology with the intimate search for life. Are the great voids silent because they are empty of life? Or are they silent because they are the perfect hiding place for civilizations that have mastered their lonely, stable domains? The answer will not be found by mapping the emptiness alone, but by listening to it. Our search for extraterrestrial intelligence now must turn its ears toward the great dark, wondering if the ultimate mystery of the cosmic void is not one of absence, but of a presence too patient and too wise to make a sound. From the search for silent life to the echo of the first sound, our journey through the cosmic void has revealed a cosmos far stranger and more dynamic than we ever imagined. We began by staring into the great nothing of the Boötes Void, a staggering emptiness that challenged our very models of the universe. We encountered the ghostly cold spot, a potential bruise from a collision with another reality. We discovered that we might be living inside a void ourselves, the KBC Void, skewing our perception of cosmic expansion. We saw how these empty regions act as dark energy's primary engine, how they hide the universe's missing atoms, and how they host strange, isolated galaxies that live by their own rules. We learned that emptiness has a hidden hierarchy, a fossilized structure that may hold the imprint of primordial gravitational waves. We grappled with galaxies spinning in eerie unison, with the possibility of exotic particles hiding in the quiet, and with the warping of time itself. We explored voids as cosmic accelerators, creating the most energetic particles known, as deserts mysteriously devoid of dwarf galaxies, and as the frozen echoes of the universe's first thunderous sound waves. We even dared to consider that our entire universe might be a single bubble in an infinite metaverse. We watched light bend around nothingness, contemplated the last shadows of the cosmic dawn, and traced the great conveyor belts of matter flowing from the void. We found orphaned globular clusters, cosmic tombstones adrift in the dark, and discovered that the largest voids are paradoxically the hottest. We questioned the very definitions we use to map reality, and faced the terrifying possibility that these voids will one day orchestrate the Big Rip, the ultimate end of all structure. Finally, we listened for the ancient whisper of hydrogen from the Dark Ages and uncovered an anomalous void from the cosmic past, a structure that defies the timeline of creation itself. What was once thought to be mere, passive emptiness is now understood as a dynamic and crucial component of the cosmos. These voids are not empty. They are reservoirs of lost matter, laboratories for fundamental physics, archives of primordial history, and the architects of cosmic destiny. They hold the keys to understanding dark energy, the nature of the Big Bang, and the final fate of everything we know. So the next time you look up at the night sky, do not just look at the points of light. Look at the vast, dark spaces between them. Ponder the great nothing, for it is there, in the profound silence and the immense dark, that some of the universe's greatest secrets are waiting to be found. We would love to hear what you think. Which of these 25 mysteries captured your imagination the most? Share your thoughts and your favorite cosmic enigma in the comments below.